Everybody, Mr. Mack here. I hope you're all doing well. This next set of notes here is on compound interest per year, and you just did a section on simple interest. And the simple interest equation that I showed you in the video that I made was A equals P times 1 plus R times T. Now, in this unit right here, there are different variables that I'm using that mean the exact same thing. So I just want to point those out. Now, let's see, we're going to call that's going to be blue. And I would have liked to have redone this, but I've had no time this week to do that. But this was the formula that we used, where A was the amount that we got after we invested a certain initial amount, which was the principal P, R is the rate, and T is the number of years. So we're going to tweak the same equation here just slightly. And we're going to have some different variables here. And I prefer the ones that I showed you in the previous video, but we're going to just switch them out for right now, and I hope that's okay. So we're going to call FV the future value right here, FV. And PV is the present value. So we called this just P on the last time, and the future value we called A for amount, and I is the interest rate, and we used the italics lowercase r before for interest rate, and the T time is the same. So when we do compound interest per year, what happens is that we'll invest our principal for a certain rate, and at the end of the first year we get our interest off of that. What then happens is that interest rate then goes back into the equation and counts for our new principal. And so we have a little bit more money that we are taking that interest with. And so the money is growing faster than just with simple interest. And so as you see, the main difference in the equation, instead of doing 1 plus r times t here, we do 1 plus I, which we call this r, so the rate here, raised to the t power. So we're raising the exponent here to the t instead of multiplying, and that's going to give us a bit more money. So right here we can see compute the amount ending in account for 1, 2, 3, 4 years. And the initial deposit is $100, so that's our PV value right there is 100, and 3% is our compound interest, and that is our I value, or R that we called it before. Okay, so that's 3%, and we're looking for what the future value is, right? So what amount is that going to be after these years for t equals 1, 2, 3, and 4? So we see here, this first one right here, 103, that would be the same as if we did the simple interest. Now we see it's just $3. Now if you remember, in the last practice that we did, that after 2 years, you would still just get that $3. So it would be, with simple interest, it would be $3 after the first year, you would get $3 after the second, it would be $3 on the third and $3 on the fourth, because it goes back to the original principal, or the initial deposit. And so 3 times 4 is 12, and we would get $112. That would be the amount after 4 years with simple interest. Now we see right here, after 1 year is 103, but 2 years it's 106.09. We got this additional 0.09 now that we didn't have previously, because 3 plus 3 is 106, and we would have been at this point right here, right? This would have been 106 here. And now we're going to see that the next year is 109.27. So, and then finally, you could see the 55 cents. We're 55 cents richer here than if we did just simple interest. And this might seem like not a lot, but if we were to increase our initial deposit here, and maybe we had a higher interest rate and we went for a longer period of time, it's going to make a huge difference. Okay? So in example B here, how much will Kyle have in a savings account if he saves $3,000 at 4,000 compound interest for 10 years? Okay, so look, basically we just have a different equation here, right? And there's no extra work in a problem like this. We have our FE, and if I wanted to write this in the way I had before, I could say A equals, and then we had our principal P, and then times 1 plus the rate was R, and we're going to put that in blue maybe, and we're going to raise that to the T power. So this is actually the way I wanted to write it, because this is the way we normally see it, but in this ebook that I got, it's used slightly different variables. And so 3,000 times 1 plus 1.04 to the 10th power, we could just put that into our goodness, where did my that's Charlie Brown. Is it there? Where is it? Okay. Web 2.0 calculator. And 3,000 parentheses 1 plus 0.04 raised to the 10th. Back that up. I didn't get that in. Raised to the 10th. Is that what I want? And 4,440.73. Yep. Okay. So, yep, that's it. Now, there's an interesting little investment trick here. How long would it take money to double if it is an account earning 8% compound interest? So there's an estimated solution here. It's called the Rule of 72. And it's just a quick calculation on how long you can figure out you can get your money to double. So 72 divided by I here would tell you approximately how much time your money would double. Okay, so I in this case is 8, so 72 divided by 8 is 9 years, right? So if we had, say we had an account in 4%, and say we're putting $1,000 in at 4%, and we say, okay, how many years will it take to double that to 2,000, for instance, right? So we would do 72 divided by 4, and that's 18. Okay, so it would take 18 years for that amount to double to 2,000, right? That's what that means. And that's just a quick trick, okay? Now, here's the exact solution here. And I want to show you, okay, so I'm finding this by using some logarithmic rules, but I think I want to show you another way as well. We could do this. So we have our future value equals our principal value here times 1 plus I to the t. And so we got 200 and 100. And look, you can see I've just substituted everything in there from the problem. And we are solving for t right here. Okay, so what is t? And so I can divide 100 to both sides, and I get 2 on the left, and I get this 1.08 to the t power, right? Because 1 plus 0.08 is 1.08. And now there's some log rules that we could use here. And we could take the log of both sides, and there's a trick here where we know that log base b of m to the n is equivalent to n times log b of m. But how about, so we could do that, and I have no problem with that. Just get rid of my head there. But we also can just use our understanding of logarithmic rules, right? So if I just take this over here, 2 equals 1.08 to the t power. So let's write this as a log, right? So the exponent is t, all right? So t is going to be, say I put this on the left side, and it's going to be equal to, now here's the base is 1.08, so we're going to say log, and we're putting the base as 1.08, and then 2 is what we're taking that of. And then log base 1.08 of 2. And here we go. We can go into our, so I can show you how to do this in a calculator too, but I'm going to say right here log. Now it says logarithm x to base 10, or there's another way we can do this on here. So maybe do I blow it up? What do I do here? I'm just trying to remember. Log, okay, or log x, something over here. Come on now. Okay, I think what we're going to do is we're going to say log of 2, comma, and then we put the base. And we'll know if it writes it on the preview. Yeah, that's what I want. I want log base 1.08 of 2. Some user error here. Okay, equals 9.0064. So 9.006, right? And this is years. Okay, so I mean 9 was a pretty good estimation, right, from our rule of 72. We ended up getting 9 here, didn't we? So that's nice. And I think maybe for you guys this is an easier way to solve it, just the way I did here on the right. But we could use these log rules for that. Okay, and oh yeah, so concept revisited here, and I kind of just explained this previously. Comparing and contrasting simple interest and compound interest. So $100 for 50 years at 6% versus a compound versus 6 simple. So you know, the simple we have 100, and this is 1 plus 50 times the 0.06. So this is the t times the rate, and then this one is the time is rate as an exponent here. And wow, I mean, look at the difference. 400 for simple, and then the compound interest is 1,842. And the difference is 1,442. That's fairly significant. Okay, so some guided practice here. Here's 3 problems, and then I think I'm going to let you guys see if you can figure out some of the practice on your own. And I don't know if I can get solutions out to you for right now. So help each other out with this. How much will Phyllis have after 40 years? Okay, so we got T is 40, and she's going to invest $20,000. So this is our principal. Our present value is $20,000, and we have 1% compound interest. Wow, that's a terrible interest rate right there, but that's the problem. So our rate here of interest is 0.01, written as a decimal. So we'll just pop it all in here, right? Future value is 20,000 times 1 plus 0.01 raised to the 40th. And I can add these together, and I'm going to pop this into my calculator, and this is what I would get. So I encourage you to try this to see how this works, right? Use your calculator and see if you can do these things. I use the caret right here on the calculator to raise to something that's other than 2. It's just much easier that way. All right, how long will it take money to double 6% compound interest? Okay, rule 72 says we do 72 divided by 6. Well, that's 12 years. It's going to take 12 years to double that. So we can solve this here using our equation. We have our future value equals the principal here times 1 plus I raised to the t. We're looking for t here. So I'm going to pull a little branch over here to the right. Okay, and so I divide by 100 to both sides, and you see I get 2 on the left, and then I get 1 plus 0.06 raised to the t. So I'll just pop this over here. I got 2 on the left equals 1.06 to the t. And let's just take this exponent, exponential form here, and we'll write it as a log. So I could say, okay, t is my exponent equals log base 1.06 of 2. And we're going to put that in our calculator. Here we go. We got log. And first we type in with this program anyway, we type in the 2 and then the base, which is 1.06. And see the preview confirms that we wrote this correctly, and I'm going to hit equal. And I got 11.895. So t equals 11.895. And you know, if we round this to something a little more reasonable, how about 11.9? This is years. Okay, about 11.9 years it would take to double, and with our quick estimate, it was 12. So that's the reason why it's called the Rule of 72. Okay, and this last one here, what compound interest rate, okay, looking for I, is needed to grow 100 to 120. So 120 is our final value, and 100 is our principal that we're starting with. And then we're saying 3 years, so we have raising to the 3. Okay, so we need to peel away everything to get I isolated. First step, divide by 100. And then, so 120 divided by 100 is 1.2. And then how do we get rid of this cube here? We take the cube root of both sides. So the cube root of cubing cancels this out. And I get 1.2 to the 1/3 equals 1 plus I. And then I subtract 1 over here. And notice I didn't go to the calculator on this step. I'm just going to wait and try to do most of my calculations on these steps. At the end, it just makes for less carrying over answers with lots of decimals in them. So we got 1.2, and I'm going to raise that to the, remember, we can express a cube as a fraction here. 1 divided by 3 minus 1. 1. And is that what I want to do? Yep, that looks pretty good. Equals 0.06265. There we go. And that is equivalent to about 6.27% as an interest rate. Okay? All right, very good, everybody. I hope that makes sense. I hope the different variables here work for you guys. And, you know, sorry I couldn't be with you this week. But you know, if you have any questions on any of this stuff, we're going to be able to hit it in the next class. Okay? Thanks a lot.